That file exists. Cat can read it. The OS knows it's there, but ls says it doesn't exist. No root, no kernel module, no exploit. One environment variable. By the end of this video, you'll understand exactly how this works, why Linux ships this feature on purpose, and how the same mechanism is used by both professional debugging tools and real-world rootkits. Before we touch LD preload, you need to understand something. When you run ls, it doesn't do everything itself. It borrows code from shared libraries, mainly glibc, the GNUC library. Things like readdir, strcmp, printf. ls doesn't implement any of those, it just calls them. The library code lives in a separate file on disk and gets loaded into memory when ls starts. Before we move on, if this kind of content is your thing, make sure to like, share, and subscribe. It helps more than you think and keeps this content coming. There are two ways to build a program. Static linking bakes all the library code directly into the binary. One file, self-contained, runs anywhere. Dynamic linking keeps the library code separate. The binary is smaller, but it needs those libraries present at runtime. Almost every program on your Linux system is dynamically linked. LDD shows you every shared library a binary depends on. ls depends on libc, libselinux, and the kernel's virtual dynamic shared object. Every function call ls makes to those libraries goes through this mechanism. When you execute a dynamically linked binary, the kernel doesn't run your program first. It runs the dynamic linker, ld.so. The dynamic linker's job is to find all the required shared libraries, load them into memory, and resolve all the function symbols before your program gets a single instruction. LD preload is a way to talk to the dynamic linker before it does any of that. LD preload is an environment variable that tells the dynamic linker, load this library first, before everything else. Before glibc, before libselinux, before any of the program's actual dependencies. And here's the critical part. When the same function name exists in multiple loaded libraries, the first one wins. So if your library and glibc both define reader, the dynamic linker uses yours. Every time ls calls reader, it gets your version. Glibc's version never runs. This is the simplest hook you can write. We're replacing strcmp, the standard string comparison function. Our version does two things: prints what's being compared, and always returns 0, which means equal. The -shared flag tells GCC to build a shared library instead of an executable. -fpic means position-independent code, required for shared libraries because they can be loaded at any memory address. We set LD preload to our library and run the password checker. Type anything. Access granted every time. The program never changed. The binary on disk is identical. We just intercepted the one function call it relied on to make its decision. Now here's where most people get tripped up when they write their first real hook. What if you want to call the real function from inside your hook? You can't just call readdir, that's your own function. You'd recurse forever and crash. You need a pointer to the real readdir. DLSim with RTLD next says, find the next definition of this symbol after the current library in the load order. In other words, find the real readdir in glibc. We store it in a function pointer the first time the hook runs. Then we can call through to the real implementation whenever we want. This is the pattern you'll use in every serious hook you write. This is the complete file hiding hook. We replace readdir, we call the real readdir in a loop. For every entry it returns, we check the file name. If it's not secret.txt, we return it normally. ls sees it. If it is secret.txt, we skip it and ask for the next entry. ls never receives that entry. As far as ls is concerned, that file was never there. ls sees 3 files. Cat reads secret.txt fine. Now we inject the hook. ls sees 2 files. Secret.txt is gone. But cat still works, because cat doesn't use reader. It uses open and read. We only hooked reader, so only programs that enumerate directories are affected. Everything else works normally. The file is perfectly readable, just invisible to anything that lists directories. I want to be clear about something. LD preload is not a hacker trick. It is a core feature of the Linux development ecosystem, and some of the most important tools in existence use it. Valgrind uses LD preload to replace malloc, free, and every memory allocation function. Every time your program allocates memory, Valgrind's version runs first, records the allocation, checks for buffer overflows, and tracks whether you freed it. When your program exits, Valgrind tells you exactly which allocations were never freed and on which line of code they happened. Without LD preload, this would require modifying your source code or recompiling with special flags. Fakeroot uses it to let package builders run install scripts that think they have root permissions without actually having them. libfaketime lets you test how your application behaves on New Year's Eve 1999 without changing your system clock. These are production tools used by major Linux distributions every day. Everything we just described works identically when the intent is malicious. A rootkit is software designed to hide an attacker's presence on a compromised system. LD preload rootkits are one of the oldest and most well-documented techniques in the attacker playbook, precisely because the mechanism is so clean. A complete LD preload rootkit typically hooks readr to hide its files from ls and find. It hooks the functions that read proc net TCP to hide its network connections from netstat. It hooks readr again on proc to hide its process from ps and top. From a normal user's perspective, the system looks completely clean. The attacker's backdoor, their files, their network connection, all invisible through normal tools. There are 3 ways to detect this. First, check the environment. LD preload has to be set somewhere. Check the process environment directly in /proc. Second, use a statically compiled binary. BusyBox compiles everything statically. It doesn't use dynamic linking at all, so LD preload has no effect. If BusyBox ls shows files that regular ls doesn't, something is wrong. This is the thing about Linux that I find genuinely fascinating. The same primitive, intercept a function call by loading a library first, is used by Valgrind to make your code safer, and by rootkits to hide from your sysadmin. The OS doesn't know the difference. The dynamic linker doesn't care about your intent. It just loads what you tell it to load. The feature is neutral. The knowledge is neutral. What matters is which side of the table you're sitting on. Want to level up and hang out with people who actually get it? Jump into our Discord and become part of the chaos. The good kind. Curious to go deeper? The full breakdown is waiting for you on the blog. No fluff, just the good stuff. And hey, if this video didn't waste your time, smash that like button and subscribe. More content is coming, and it only gets better from here.